So hi everyone, so we are from group 1 of heat integration, and today we would like to share with you our solution for a heat integration problem. So as you can see here, this is the information given to us. We have the temperature supply and the temperature target in degrees Celsius, followed by the heat load. So our first step is to extract the data. Alright, as you can see here, we've identified the hot streams and the cold stream. So as you can see, the hot stream is identified by the stream that has a higher supply temperature compared to its target temperature, and followed by that, using the load and using the change in temperature, you can find the value of Cp. Okay, Cp is the flow rate, flow of the stream. Okay, so the Cp value can be determined by dividing the load with the change in temperature. So in this case, like it's 1000 kilowatt divided by by 100 degrees Celsius, so you'll get a Cp value of 10. The next step is to find the adjusted temperature interval. So in our example here, we are using a temperature delta T minimum of 20 degrees Celsius. So how it works is that for all the hot streams, the temperature will be will minus with half of your delta mean. So in this case, because the delta mean is 20, so every hot stream's temperature will be subtracted by 10 degrees Celsius, whereas every cold stream temperature will be added by 10 degrees Celsius. So the markings in the pencil here are the adjusted temperature. So as you can see here, in this first hot stream, the 300 here, we subtract it by 10, so that's why you get 290, and followed on by this stream 200, we get 190, and the same goes for this cold stream, we add 10, and that's how you get the value. So once you have done this part, you'll now move on to the temperature interval part. So in this particular section, what you want to do is that you want to first divide it according to the adjusted temperature interval. Okay, so then what you do is for every single data, so you know, for example, the first stream is 290 to 190, so you just draw a line from 290 all the way to 190. Okay, and you repeat it for all the 6 streams. The next step after you have done this is to determine the interval. Okay, so the interval here, for example here, the first interval between 290 and 240 is the first interval. There is a delta T of 50, 290 minus by 240. And how do you determine the Cp value? Okay, is by looking at the interval here. So in this particular interval, there's only one stream which is present in the interval here, which is this first stream with a Cp of 10. Okay, so then you find out what is the delta H, which is Cp multiplied by delta T. Okay, now what if there is more than one stream in this particular interval? Like let's just say in this interval we have stream 1 and stream 6. So in this case, what you do is that you take the Cp of hot minus by the Cp of cold. So this, you have to be consistent. Okay, so in this case, so in this particular temperature interval between 240 to 200, we have 2 streams. So this is hot, which is 10, minus by 25. So that is why in the second interval, our Cp value is minus 15. Okay, so then we just repeat this process up to the last temperature interval, which is the 6th temperature interval. Now once we have this, we will then move on to our cascade. Okay, so now for the cascade, what we want to do is to just add or subtract the delta H for every single temperature interval. So in this case, our first temperature interval has 500. Then in the next temperature interval, it goes to negative 600. So what happens is that because we start with 0 and we add 500 kilowatt of enthalpy, you get a remainder of 500. So this is what we add, and this is what that remains in the system. Okay, so 500, and then when we're moving from interval 2 to 3, you need to, from interval 1 to 2, you need to minus 600 kilowatt. So when that happens, you have a remainder of 1000. You have a deficit of negative 100 kilowatt. So you just repeat the process, make sure your unit, your signs are correct, and you'll end up So what will happen here is that you must observe the remainder energy here. Why is it so? It's because we want to see what is the deficit. So the ones in negative are the deficit, and this is not good. Alright, we do not want any deficit energy in our cascade. So in order for us to make the remainder energy in our system here to be in surplus, we just identify the most negative, the biggest negative value in our cascade, which in this case is negative 1000. So we know for a fact that because of this negative 1000, if by removing this negative 1000 kilowatt in our system, we'll be able to have a system in surplus energy. So how do you do that? Is that you just add this 1000 back to the start. So then you begin with 1000, and then you just follow the same process. So 1000 plus with 500, 1005, minus 600, 900, etc. And you'll notice that at one point when you're completing this whole, there's two observations here. First of all, you should not find any negative sign. You should not have any surplus of energy after your after you've done your feasible cascade. And the next thing is that you should find a point where the remainder energy here is 0. At this point, you will find your pinch temperature here. Okay, so in this case, this is the third interval, right? So as you can go back and see, your third interval temperature here is 190. Okay, so 190, in this case 190 is your pinch temperature. So what are the other things you can observe here is that once you've already gotten a 0 here, so this is your pinch interval, and you have a surplus energy, remainder of energy, you will then know your minimum heating utility requirement and your minimum cooling requirement. So that is all regarding the problem table algorithm on how to determine your minimum heating and cooling values. So after we have done the problem table algorithm, we have done the adjusted composite curve. So you can see here, this is the hot stream and this is the cold stream. Okay, so when the delta T mean is 10 degrees Celsius, we notice that there is no heating utility, and there's no cooling utility, and there's no heating utility. Okay, and another thing which we can observe here is the pinch point. In delta T mean 10, our pinch point is 195 degrees Celsius, but when we compare with other delta T mean, like in this case this is delta T mean 20 degrees Celsius, the pinch temperature is 190 degrees Celsius. For delta T mean 30 degrees Celsius, the pinch point is at 180 degrees Celsius, 180 degrees Celsius, and then at delta T mean 40 degrees Celsius, we have the pinch point at 180 degrees Celsius. So for every increase of delta T mean by 10 degrees Celsius, the pinch point reduces by 5 degrees Celsius. We then did the grand composite curve. The grand composite curve is a way to show the streams, the hot and cold streams, with relation to its respective heat load, and it's also give us an indication of how we can actually add our utilities. So like for when delta T mean equals to 10 degrees Celsius, there is no heat or cooling utilities needed, as the process to process integration is able to provide heat to its respective streams. If we were to use a delta T mean of 20 degrees Celsius, so for heating utilities, we will need to consider from this point up to this particular point here. This is 1000 kilowatt. So using this particular data, we can then decide what type of utilities to use. For example, we can use low pressure steam to provide us the necessary energy to increase the temperature from this point to maybe up to this point. Okay, and then maybe then we can use high pressure steam to increase the temperature of the stream from this point to this point. And it's also the same for the cooling utility as well. So this is the grand composite curve for delta T mean 30 degrees Celsius. As you can see, with the increase of delta T mean, our required utilities also increases. And this is for 40 degrees Celsius. So that's basically it on our explanation of how we have done the problem table algorithm, the composite curve and the grand composite curve. Thank you.